Let's continue our discussion of solids of revolution with the shell method. So we're going to discuss the shell method for computing the volume of a solid of revolution. Suppose we have a solid of revolution that is a cone. A cone is a solid of revolution given by a function that is a line. So this is just a right cone. Okay, in the shell method, or let's say first in the disk method, we would have sliced this cone into disks that were tall ways in this coordinate system, and then added those disks together in sequence. To calculate the volume using the shell method, we're going to use not disks, but we're going to use cylindrical shells. So suppose that I have a shell here. Okay, there's one shell. And so I'm going to be adding up the volumes of shells like these to get the volume of my cone. You might be wondering, well, how can I possibly get the volume of the whole cone from cylinders like that? Well, let's consider starting out with first a really small and long cylinder, and then our next cylinder would be a little shorter and wider. The next cylinder even shorter and wider. And you can see that given some number of cylinders that look like this, I will be able to approximate the volume of this cone. So we're adding up cylinders that look like this. Here's one example of a cylinder. So let's go ahead and look at the volume of a cylinder like this, a cylindrical shell. Okay, so here's our cylindrical shell. It's hollow. The wall of the cylindrical shell has a height, or has a width, let's call it W. If I consider the radius of the shell as the distance from the axis of rotation to the center of the shell, and call that P, then I can say that the total volume of the shell, which is given by the outer volume minus the inner volume, is, well, if the outer volume is the volume of the outer cylinder, that should be pi r squared h, where r is the radius of the outer cylinder. The radius of the outer cylinder is p plus w over 2, so the volume is pi times p plus w over 2 squared times h. In the same way, the volume of the inner cylinder is pi times p minus w over 2 squared h. And so the volume of the shell is pi times p plus w over 2 squared h minus pi times p minus w over 2 squared h. Let's factor out the pi and the h, maybe make those brackets. Then we can simplify the inside by expanding those binomials. Okay, when we do that, we get pi times, let's just expand these, we get p squared plus pw plus w over 2 squared minus p squared, and then minus a minus, so plus pw, and then minus a positive w over 2 squared times h. So the p squares cancel out, w over 2 squareds cancel out, and we're just left with 2 pw's. So we get 2 pi times pwh as the volume of this cylindrical shell. Now, considering that back in the context of our function. Okay. Since our representative rectangle is horizontal, we're going to need to consider this as a function of y and not a function of x. The radius p is going to be a function of y. We'll call that f of y. So we're going to let p, our value from before, be f of y. The width that we discussed before in terms of our representative rectangle is the change in y, the incremental change in y. So w is delta y. And then h is also a function of y. I'll call that just h of y. In fact, let's just call this p of y. Okay. And so the incremental change in volume that I'm going to be adding up to make my integral is going to be 2 pi times p times h times w. So I'll get 2 pi times p of y times h of y times delta y. And then if I add an infinite number of infinitesimally small increments, I get that my overall volume is going to be the integral of 2 pi times p of y times h of y with respect to y. And I'm going to move that 2 pi out to the front of my integral since it's a constant. Okay, so this formula gives us the method, the shell method for computing the volume of a solid of revolution using cylindrical shells. Okay, I've given this formula in terms of y for horizontal shells, let's say. Maybe that's a bad word. Let's say shells made from horizontal rectangles. If my shell is made from vertical rectangles, then these are going to be functions of x's. My integral is going to be taken with respect to x. This would be a shell from vertical rectangle. All right, so let's do an example of a shell from a horizontal rectangle. Hold on just one moment. Okay. Consider the shape, let's see. Let's do this one. Consider the function f of x given by x minus x cubed. If I graph that function, I get a graph that looks like this from 0, and this point is 1. And I want to find the volume of the solid of rotation when I rotate that shape around the around the y-axis. So that solid of revolution would look something like this. Maybe like the top, kind of like the top half of a donut that doesn't quite have a hole in the middle. Okay, so my shells for the area, excuse me, the volume that I'm adding up are going to be vertical shells, since when I rotate those vertically, I get a cylinder. Okay, in this case, the height of those shells, or h of x, since my function is a function of x, and my representative rectangle is a vertical one, I'm using a function of x. My h of x is just the height of the function. So in this case, oops, it's not x, it's f of x, which is x minus x cubed. That was the height of my cylinder. And then I also need to consider p, the function p, which is the distance from the center of the cylinder to the middle of the representative rectangle, which if the height of the rectangle is h of x, or excuse me, f of x, then the value of p of x is just simply x. So then the volume of this solid of revolution is given by 2 pi times the integral from 0 to 1 of p of x times h of x times dx. So let's compute this integral. The antiderivative of, well, let's distribute first. So I get x squared minus x to the 4th dx. The antiderivative of x squared minus x to the 4th is x cubed over 3 minus x to the 5th over 5, and I want to evaluate that from 0 to 1. I forgot my pi. And so I get that this is, the volume is 2 pi times 1/3 minus 1/5, which, skipping over some algebra, is 4 pi over 15. Okay, let's do another example. Let's use the function we're just going to use an explicit function of y, x equals e to the negative y squared. Okay, and we're going to rotate this function, or at least we're going to rotate the area between this function and the y-axis about the x-axis. So the x-axis is our axis of rotation, so our representative rectangles then to make up our shells are going to be horizontal. There's one drawing of one such shell. Okay. The width of my shell is delta y. The height of this cylinder is my function e to the negative y squared. Okay, and then p, which is my radius, p of y is simply the y value at which I'm evaluating that function. So p of y is just y. So I get the volume of this shape going from, oops, and I didn't mention my bounds of integration, going from 0 to 1. So the volume of this shape, which looks something like this, kind of like a really thick shield, or a thick something with a mound on the side. Here's the axis of revolution. Okay, the volume would be given by 2 pi times the integral from 0 to 1 of h times p. So that's going to be y times e to the negative y squared dy. The antiderivative of e to the negative y squared is, well, let's use u substitution. If I let u equal negative y squared, then du is equal to negative 2y dy, and so du over negative 2 is equal to y dy. Thankfully, I have a y and a dy there, so I can write that v is equal to 2 pi times 1 over negative 2 times the integral, and I'm going to leave the bounds of integration out for now, times e to the u du. Okay, so I get negative pi, let's see, negative pi times e to the u is my antiderivative, and I'm going to replace my u. I'm going to back substitute negative y squared. Then I can add back my bounds of integration, which were from 0 to 1. And so I get that the volume is equal to pi times 1 minus 1 over e, which is approximately 1.986. But this is a sufficient answer. It's actually better than that one. Okay, so let's look at a comparison of the disk and shell methods, right? So first we're going to consider vertical axes of revolution. So for a vertical axis of revolution, you could use either the disk method or the shell method. So I'm going to present both, or how we would tackle each, if it was more convenient for us to do any of those. Alright, so we're going to have some arbitrary function of x and y. Let's suppose that function has bounds of x equals a and x equals b, and then we're considering an area between y equals c and y equals d, and we're going to do that for both cases. Okay, so for the first one, we are going to consider the disk method. So for the disk method, if our axis of rotation is vertical, that means our representative rectangle is horizontal, so that it can form a disk, or in this case, it forms a washer. So our washer rotates that way. And so the integral, or the volume of that object, is given by pi times the integral from c to d of the major radius squared minus the minor radius squared, and that integral is going to be taken with respect to y, because my representative rectangles change with respect to y. Okay, in this case, my minor radius is this distance here. My major radius is this distance here. Okay, so again we have a vertical axis of revolution. And suppose we want to use the shell method. Or it's more convenient for us to use the shell method. We'll talk about an example in a second when it actually is more convenient to use the shell method. Using the shell method, I get representative cylinders. So there's an example of a representative cylinder, cylindrical shell. Okay, this is going to be written as a function of x. Okay, I'm concerned with the height of my cylindrical shell, the distance from the axis of rotation to the center of my cylindrical shell. Okay, the width of that shell is delta x. And so the volume is going to be given by 2 pi times the integral from a to b of p times h times delta x, or with respect to x. Okay, these two volumes are of the same shape, so they should be equivalent. They are equivalent. So it's for a vertical axis of revolution. So let's take a look at horizontal axes. So for a horizontal axis, oops, that's not an abbreviation. We're going to use the same arbitrary function, okay, and the same bounds as we did in the previous demonstration. So we'll let that be A, B, C, and D, A, B, C, and D. Okay, and then suppose this time we're rotating about a horizontal axis. For the disk method, or the washer method, in order to make a disk, we're going to need a vertical representative rectangle. Okay, so we're going to have a minor radius r, and we're going to have a major radius capital R, and the width of that rectangle is delta x. And so let me turn that light back on. There we go. And so the volume of the shape is given by v equals pi times the integral from a to b of the minor radius minus, or excuse me, the major radius minus the minor radius, and that integral is taken with respect to x, since we have a dx, or delta x. For the shell method, in order to make cylindrical shells with a horizontal axis of rotation, there's my cylindrical shell, my representative rectangle has to be horizontal. And so I'm going to have a height, delta y. I'm going to be concerned with the radius of my shell, p, and I'm also going to be concerned with the height of my shell, h. And my volume v is going to be given by 2 pi, the integral from c to d, 2 pi times the integral from c to d of p, h, and that integral is going to be taken with respect to y, since I have a delta y. So let's look at the function, one function we did last time. We looked at the solid of rotation formed by taking the area between the function x squared plus 1 and the lines x equals 0, x equals 1, and y equals 0. So here's the area again. Okay, last time we split it into two regions. We didn't have to actually use two integrals, although we might have. One of the integrals would have just been very easy, but we just used the formula for the volume of a right circular cylinder in the bottom. However, using the shell method, if we use the shell method, we do not have to use two integrals. We can do this with just one integral. Okay. So we're concerned with p of x as a function